In previous sections, we have used basic trigonometric functions to solve right triangles. In this lesson, we will learn how to use the same basic trig functions to solve oblique triangles, or triangles with no right angle. Two laws used to do this are, first, the law of sines, which we will learn now, and second, the law of cosines, which will be highlighted in the next section.
The law of sines shows that the sides of a triangle are directly proportional to their respective opposite angles. The formula, based on the triangle shown below, is sine A over A is equal to sine of angle B over B is equal to sine of angle C over C. The proof is fairly simple. Using the formula for the area of a triangle, using all three sides, you get 1/2 BC sine of angle A is equal to 1/2 AC sine of angle B is equal to 1/2 AB sine of angle C. If you multiply each area by the expression 2 over ABC, you'll be left with the formula shown above. There are three parts of a triangle that are required before you can use the law of sines to determine the remaining measurements. There are four cases for these three parts of information. In case 1, you're given one side and two angles. In case 2, you're given two sides and one angle. In case 3, you're given two sides and the included angle. And in case D, you're given three sides. Only cases A and B are cases where you can use the law of sines. Now let's look at a simple example problem for case A, one side and two angles. Looking at the illustrated triangle below, solve for the length of side BC. Using the formula for the law of sines, we find that sine B over AC is equal to sine A over BC. Angle B must measure 65 degrees. We can then plug in for our angles and find sine 65 over 10 is equal to sine 55 over BC. Solving for BC, we find that BC is equal to 9.04.
In this problem, we will cover the side-side angle, one solution case. Imagine we have a problem like this. Solve the triangle ABC where angle A equals 45 degrees, side A equals 5 root 2, and side B equals 5. We will use the law of sines to solve for angle B first. With a little algebra, we can come to the conclusion that the sine of B equals 1/2, so B equals 30 degrees or 150 degrees. Knowing that the measure of the three angles in a triangle equals 180 degrees, we can rule out 150 degrees and determine that angle B equals 30 degrees. Continuing with this problem, we have to look back at what we know. We know that angle A equals 45 degrees, side A is equal to 5 root 2, and side B equals 5, and we just determined that angle B equals 30 degrees. After quickly solving for angle C with a little bit of arithmetic, we can determine that angle C equals 105 degrees, and then we can again use our law of sines to solve for side C. Again, with a little more arithmetic and use of our trig functions and a little help from our calculator, we can determine that side C equals 9.659. With these measurements, we can find a triangle that looks something like this. For our next problem, we will deal with the side-side angle ambiguous case. In this ambiguous case, there are three possible solutions that can occur. The first being that no triangle with the given information exists. The second, one such triangle exists with this given information. And the third and final, two distinct triangles may be formed that satisfy the given conditions. And these three cases are shown below. Say we're given a problem that looks like this. Solve the triangle ABC where angle A equals 30 degrees, side A equals 6, and side B equals 10. In this problem, we will hold out the sketch because the SSA ambiguous case could give us problems in sketching our triangle. Again, we'll start with a law of sines to solve for angle B. With a little arithmetic and help from our trig functions, we determine that the sine of B equals 5/6 and B equals 56.44 degrees or 123.56 degrees. With our knowledge of the sums of angles of triangles, we can determine that both of these angles are candidates for angle B. So going back to what we know, angle A equals 30 degrees, side A equals 6, side B equals 10, and we just solved for angle B, which is either 56.44 degrees or 123.56 degrees, which with a little arithmetic we can solve for our angle C, which would be either 93.56 degrees or 26.44 degrees. With some help from our law of sines, we can again, our side C, when angle C equals 93.56 degrees, our side C equals 11.98. When our angle C equals 26.44 degrees, however, our side C equals 5.34. With our various sides and angles, we can come up with two different triangles that would look something like this.
Finally, let's look at an application problem. A rocket is launched from point A at a 30-degree angle from the ground. Another rocket is launched from point B at a 70-degree angle from the ground. Point A and point B are 60 units away from each other. Unfortunately, the rockets collide at point C in a fiery explosion. Due to their self-propulsion, their flight paths remained at the same angle throughout their flight. Calculate the distance to point C for each object from their launching point. To find the two distances, AC and BC, we will use the law of sines. Using the formula, we find that our two equations are sin x over AB equals sin 30 over BC, and sin x over AB equals sin 70 over AC. But before we can solve for BC and AC, we must find the angle x. Using the definition of a triangle, we know that 180 must be the sum of all the angles of the triangle. If we solve for x, we find that it is equal to 80 degrees. Next, we'll plug that value for x into the two equations and solve. Our two equations are now sin 80 over 60 equals sin 30 over BC, and sin 80 over 60 equals sin 70 over AC. If we solve for BC and AC, we find that BC is approximately 30.46 units and AC is approximately 57.25 units.